Scientists make atomic nuclei talk inside silicon chips. Quantum computing has taken a decisive step forward. Engineers at the University of New South Wales, UNSW, have discovered how to make atomic nuclei talk to each other within silicon chips, a breakthrough that could finally unlock scalable silicon-based quantum computers. For decades, researchers have sought to harness entanglement, the strange quantum link that binds particles so closely that their states can no longer be described independently. Entanglement is the cornerstone of quantum computing's advantage over classical machines. Now the UNSW team has succeeded in entangling the spins of two phosphorus atomic nuclei embedded in silicon using electrons as mediators. The achievement, published in Science on September 18th, demonstrates that quantum states can be manipulated at the same 20 nanometer scale used in today's semiconductor industry. In practical terms, that means quantum devices could one day be manufactured with the same technology already used to produce billions of transistors in everyday laptops and smartphones, from isolation to communication. The spin of an atomic nucleus is the cleanest and most isolated quantum object in the solid state, explains Scientia Professor Andrea Morello, who has led the UNSW group for 15 years. That isolation allows us to preserve quantum information for exceptionally long times, but it also makes nuclei difficult to connect into a useful processor. Until now, multiple nuclei could only interact if they were extremely close together and coupled to the same electron, but this imposed strict limits. Only a few nuclei could fit within the electron's reach, making scale-up nearly impossible. Lead author Dr. Holly Stemp, now at MIT, describes the breakthrough in simple terms. Previously, nuclei were like people in a soundproof room. They could talk clearly to each other, but only if they were in the same room. What we've done is give them telephones. Each nucleus stays in its quiet environment, but now they can communicate over distance. In this new scheme, electrons act as the telephones. Quantum physics allows electrons to spread out in space, overlapping with nuclei at different locations. By coupling each nucleus to its own electron and allowing the electrons to interact, the researchers enabled two nuclei, separated by 20 nanometers, to exchange information. A quantum leap in scale. That 20 nanometer gap may sound vanishingly small, but in atomic terms it is vast. Stemp offers an analogy. If each nucleus were the size of a person, their separation would be about the same as the distance from Sydney to Boston. Crucially, 20 nanometers is also the feature size of modern silicon transistors. This is our technological breakthrough, Stemp emphasizes. We've shown that the most pristine quantum objects, nuclear spins, can communicate at the exact scale where today's silicon devices are built. That means we can directly piggyback on the trillion-dollar semiconductor industry. The phosphorus atoms were implanted into an ultra-pure silicon wafer fabricated in collaboration with the University of Melbourne and Keio University in Japan. The team then used precision electronics to manipulate and measure the spins, confirming the entanglement between the nuclei, towards scalable quantum processors. By eliminating the need for nuclei to share the same electron, the UNSW method clears one of the biggest hurdles in building large-scale quantum processors in silicon. Morello explains, electrons are relatively easy to move around and shape. That means we can switch interactions on and off with great precision. Exactly what you need for computation. Today we demonstrated this with 2 electrons, but in the future we can use more electrons, even stretch them into elongated shapes to link nuclei over larger distances. The work builds on earlier UNSW milestones, including record-long storage of quantum information in nuclei, more than 30 seconds, which is enormous in quantum terms, and quantum logic operations with error rates below 1%. Now, the missing piece of scalable connectivity is falling into place. A silicon-based future quantum computing remains one of the defining technological challenges of the 21st century. Competing approaches from superconducting circuits to trapped ions each offer advantages but face limitations in noise, stability, or scalability. By proving that atomic nuclei can be entangled inside standard silicon chips, the UNSW team has positioned their platform as a strong contender. Silicon has always been the natural home of classical computing, says Morello. With this discovery, It could also be the home of quantum computing. We've shown that the quietest quantum systems can now have a clear voice, and that voice can be heard across the